And now let's look at what we have in scikit-learn for doing non-parametric, for making use of non-parametric methods. So at first, for density estimation, we have kernel density estimation available in scikit-learn. We have this in the submodule neighbors kernel density. And this KDE estimation will get as parameters the bandwidth, of course, kernel width. We'll choose the algorithm. So we can make use of KDE trees, ball trees, and all these kind of neighbors, fast neighbor evaluation algorithms with kernel density estimation also. So by default, it is automatically determined according to some variables inside. So the algorithm by itself is trying to make it well optimized. And the kernel that can be used here, we have the Gaussian, top hat, Tepanechnikov, exponential, linear, cosine. So these are the different kernels that can be used for making KDE. So we have a method we can call fit on that mapping that will learn the density from the data. So we don't need labels. There's no labels here. We just give the X data set. We are fitting it. And from that, we are able to estimate, we are even able to generate samples. So with the Gaussian or top-up kernels, we are able to produce samples that have the same density, the same distribution that the data we use for learning the density. So it's nice to kind of reproduce new samples from the original ones. And we can also evaluate the log likelihood of the data. So we just give it a new data set as X here, and the score will give us the log likelihood of this data. And we can also get, of course, the density. So the P of X is available with the score samples. We have a function that we can call from that mapping. In terms of k-nearest neighbors, we have the k-neighbors classifier model, which allow us to make KNN classification. So of course, we are able to determine the number of neighbors. So the k value here is available. By default, it is using a k equal to 5. And we can, it is also optimized so that it will make use of some algorithms here. So we have KD trees, ball trees, brute force. Brute force is basically to make no optimization. It's just to recompute the neighbors for everything, so it's not optimized. But by default, it is deciding which algorithm is the best according to our configuration. And we can also modify the metric. So by default, it is Euclidean distance, basically min cos k with p equal to 2, so it's the same thing. But we have other metrics available, but I would say just look at the documentation because it's kind of, yeah, you have it from another elements that are the distance metric object. So you can plug in it a different object that will be different. They will be processed in some way. So we can get with that Manhattan, the infinity, and several others. But if we just want to move between Manhattan, Euclidean, and the infinity, we can just keep the min cos k distance, but change the p-value so we can get p equal to 1 to get Manhattan. I'm assuming that maybe not equal infinity, but we can replace this for getting the infinity by something like another distance object. So over that mapping, we can first do a fit. So the fit will be to memorize the data set with the labels, given that we may be using KD trees here. So the fit will build up the KD tree internally to be able then to classify fast other samples. Then we can get the k nearest neighbors to a given data sample. So we just give the X or the data set X, and we get the nearest neighbors, the k nearest neighbors according to the parameter we are giving. We can do prediction, so basically classify the data according to the k nearest neighbors. And that's it for that. And we even have a k nearest neighbor regression possible. So it's kind of making regression based on the nearest neighbors. This is something that we are not covering today, but that is available. And basically that's what we have to discuss today.